So in this lesson, we're going to be talking about different types of outliers, how to detect outliers in the Y space, detecting leverage points, detecting highly influential points, all using the soft drink data that we've looked at before. So our goal is to be able to identify possible outliers in the data. And we typically define outliers as an unusual data point that's kind of remote from the rest of the data, doesn't really follow the trend, and this point is going to have or the point is going to have a strong influence on the analysis. So there are different types of outliers. The ones that we're going to look at are outlier in the response or outliers in the Y space, leverage, which is outliers in the X, and then highly influential points, which are outliers in both the X and the Y. So we want to be able to identify these types of points and see if they have an extreme impact on a regression line and figure out what to do with them. And so what we're going to be focusing on in this class is using plots and diagnostics to really identify outliers and see their influence. In simple linear regression, which are going to be most of our examples, it's kind of easy to identify outliers. But in multiple linear regression, where we have multiple predictors, it's hard to evaluate a single scatter plot, like we saw in our previous notes with the partial regressions. So what we do is we use residuals for our diagnostics and our plots to understand where things are kind of going wonky. With that, let's get some pictures in here to understand what and where outliers would be under our different types. So first we need to understand kind of what the normal data would look like or what we'd expect. And this is the no outlier data. And then in the next couple of plots, I'm going to introduce different types of outliers and where they would be. So our first one is an outlier in the Y space. And so you can see this one up here with this big X. Notice that in the range of the X, this data point does follow in the range of it, doesn't look weird in the X axis. But when you look at the Y, this is pretty far out there. And so this would be considered an outlier in the Y space or the response. The other types are leverage and highly influential. So again, leverage is an outlier in the X. So, but the Y isn't so extreme. So here we can notice that in our X, most of our data kind of falls in this little area. And then we have this point up here. Now, the reason I wouldn't consider it so extreme in the Y is because if we were to kind of follow the trend of this data that we're seeing, this point is being hit. And so I wouldn't consider it extreme in the Y, but I would consider it extreme in the X because it is following the pattern that we do see here. The other type, which is the one that we want to be very careful about because it's going to have the most impact on our analysis, is the highly influential points. And so it's extreme in both the X and the Y. So here's our data, and then here is our highly influential point. And this is going to cause a lot of issues. What issues? Well, if we were to scroll down to this picture, I'm trying to demonstrate the effect of this point in and not in the model. So if we had all these black points and we fit our regression line, we would expect this. So this is fitted with only the black points. Okay. Now, if we were to incorporate or include this outlying point, our new fitted model would be this red one with X. So hopefully you guys can notice that this point by itself is causing a lot of influence on our regression model or estimating our betas. So this individual point has a disproportionate influence on our regression line. Okay. We need to know about these highly influential points, or also sometimes called HIP points, because they are going to impact our fit, our confidence intervals, our prediction intervals, and our inferences. Okay. So right now we've kind of briefly talked about the different types of outliers. Once we are able to detect that there's an outlier, we need to start to take steps to address these outliers on what to do. The first kind of thought process is to double check data. Is there any incorrect values that were maybe entered? Maybe you missed a decimal point and stuff. That stuff does happen in real data. If the value isn't correct, maybe this is a suggestion that you need to vary your experimental conditions, add a predictor or other predictors so that you are able to explore the data a little, not the data, explore the regressor space a little bit more and be able to understand it. Now, if your point or your data point is valid, but it's an unusual measurement, this is possibly a new insight. And a lot of the times, a lot of new research is based on one or two outliers because they're providing us with probably the most important and most insightful information. So don't just delete your observations. That is kind of the whole point. We're doing these double checks. If it is incorrect, okay, then you can delete it. But overall, your first step shouldn't be, oh, this is an outlier, delete. Please don't do that. There's ways around it. There are methods in which, if a point is valid and it's unusual, there are ways such as doing Cauchy regressions that can downweight the impact of outlying observations. Okay, so don't just delete your outliers. Investigate them and make sure you have a reason for your next steps. So now that we've identified the different types and we've kind of talked about some of the steps afterward, let's now go to using plots and statistics to understand and identify when we do have an outlier in our data. So the first one we're going to talk about is detecting outliers in the Y. And we're going to use our residuals for this. And hopefully you guys will notice that if you understand checking our assumptions, then this plot we're about to use should look very familiar. Again, the reason why we're looking at our residuals is because regardless of the number of parameters, so in multiple linear regression, we could have K number covariates, right? And it's hard to understand and represent that. But each new observation only has one Y, and it's only going to have one residual. So this is allowing us to reduce our data from K regressors to kind of just looking at one dimensional. So how we detect outliers in the Y space is we're going to use the residuals versus predicted. Or you can also look at the residuals versus their index, where their index is just the number that you give it as you enter the data. In both plots, we're looking for observations that don't match the pattern of everything else. And so in here, when we're using this data, we can see that this point right here, which is also our X, is way out there. Another way, or maybe a more formal way of testing this, is to use studentized residuals. So we've talked a little bit about this in our previous lessons. So we're going to talk a little bit more about this. There are studentized residuals called external and internal. So the external studentized residuals are the jackknife approach to our standardized residuals we talked about before. The internal studentized residuals is taking the residuals and dividing them by their standard deviation. This external is that jackknife approach that we've talked about before. If that doesn't make complete sense to you, that's okay. Pretty much the whole idea of using either the external or the internal studentized residuals is that we are now standardizing our data so that we can compare them to this rule of if the residual is greater than 2. Okay, the idea of this rule then comes into this, the idea of this rule comes from the empirical rule. So the idea of the empirical rule is 68% of your data will be within one standard deviation, 95% of your data will be within 2 standard deviations. And so this is saying that we would expect, if anything's kind of outside that 2 standard deviation, we might be flagging it as an outlier. Now, I would recommend not just using this rule, but also plotting your data like we did above, because we also know that, let's say we had 100 points, we would expect maybe 5 of those points to lay outside 2 standard deviations, just because of how the empirical rule works and how our distributions are. Here's how you get it in JUMP and R. Of course, I'm going to do a video for you guys. And then here, if you wanted a table, here's a table where we have our Y, our X, our residual, this is the raw, and then our capital R is our standardized or studentized residuals. In this class, I'm not going to make a big fuss. If you use either one, you should be close enough. The next outlier we're going to talk about is how do we detect leverage points. What we're going to do is we're going to use a value called the leverage or the hat diagonal. So to detect high leverage, we're going to use this value, and what it's going to do is it's going to measure the remoteness of the predictor value in the ith observation related to the other observations. A little bit of note on why we call it the hat diagonal is if you studied multiple linear regression through a more theoretical perspective with linear models, we would use matrix representation of the x's, or also called the design matrix. And so it comes into play with getting values off a diagonal of a matrix. You guys don't need to worry about that. What I want to tell you about this hat diagonal is that it solely depends on the value of the x's, and it's only going to tell us how far away from the remoteness. So this value is only solely depends on x's. Okay, so that's kind of the whole idea. Large values of this hat indicate that the ith case is distanced from the center of all the x's. The sum of the x's, or the sum of the hat values, is going to be equal to p, the number of parameters in the model. HI is determined completely by the values of the predictors. And then we have this rule of thumb right here, where we say if HI is greater than 2p over n, where p is the number of parameters and n is the number of observations, then we would probably want to flag it as a leverage point and an outlier in the x. A little intuition behind this right here is that if we were to add up all the values of the hat values, we would get p. Said that here. This is theoretical. You don't need to prove this or completely understand it, but I'm telling you, if you summed up all the HIs, it's going to equal to p. Okay. Then we also know that there will be n hat values for the number of points. So the p divided by n is the average value we would expect for the hat value, assuming everything is there aren't any outliers or anything. We would expect it to kind of lie around that number. So what the rule of thumb is saying is that if we have a hat value that is more than 2 times what we'd expect to see, we would probably flag it as a leverage point. There is a time when the rule of thumb doesn't apply, so be aware of that. And then again, you won't need to understand exactly how these are calculated, just understanding that they only depend on the x's, and then being able to get the values out of JUMP and R are important. Here, again, in our example data, where recall that our example data is this right here, we'd expect this point, which is observation 14, to have a higher leverage, and it does. What I would again recommend, and I'll show you this in our soda example, is to plot these values. Numbers are hard to compare when they're just looking at them, so you want to plot these values always. It gets you a good picture. All right, moving on to our kind of last type of outlier is the highly influential points. So how do we detect these? So recall again, the HIP or highly influential points are extreme in both the X and the Y. And there is a lot of criterions that can be used to identify these points and measure the effect on the analysis for the data set. In this class, we're going to formally cover Cook's distance. At the end of this lecture, I'm going to give you a little bit of extra documentation for these other diagnostics to maybe help you in your research. We won't be formally covering these, but hopefully maybe this will at least be like, oh yeah, I remember from Stat 5615, these are other ways we can look at it. Okay, so let's start looking into Cook's distance. Cook's distance is a measure that represents for each observation in the data how all the predictor values would change if that observation was removed from the regression. So the whole idea is we have our original fit from our regression. Then we're going to remove points. This kind of idea of removing points is known as jackknifing. Okay, remove it. We're going to look at the impact of, by removing that point, how did our kind of regression and stuff change? That idea kind of comes into play here. So when we had this point, this outlier in the data, we had this regression fit. When we removed it and we refit the data, we now had this regression line. There's a huge, I would say, pretty large impact here. And so that's the idea of Cook, is we're gonna, or at least how it's examined and how it's calculated is we're sitting there kind of removing observations and seeing how it's affecting our results. Okay, typically points with larger Cook's distance need to be examined further because they can have a major influence. Here's the formula for Cook's distance. Again, you guys won't need to know this, but I figured it's good to have for your notes. This right here is representing when we remove the ith observation. So that's what that means. Again, large values are going to indicate that we kind of have a big influence on our estimators. The values of D near 1 usually indicate high influence. So the rule of thumb is if our hit points have a Cook's distance larger than 1, we probably are going to flag it. Again, this is just a guideline. I recommend getting your Cook's influence points from JUMP or R and then plotting them. Always plot. Okay, so let's get back to our soft drink example. So in this example, we had a soda company concerned with the time it takes their employees to service their vending machines. The time is determined by the distance walked, by the route driver, and the number of cases stocked in the vending machine. In our previous lessons, I don't remember if I told you guys this, but we actually had 24 employees. What I did was I actually removed this point so that we weren't worried about outliers and all that. We were just worried about how to fit stuff and how to look at the other topics. So I put that point back in here. So that's why we now have 25 employees. Okay. So one of the first things we want to do is we want to get our residuals, get our predicted, and we can now look for outliers in the Y space. Again, probably would recommend looking at the studentized or the standardized residuals versus predicted because you have a way to compare your results. So if I was looking at this plot right here, it might be a little bit harder for me to convince myself that this really is that much of an outlier in our Y, because that's kind of not that far of a distance. But when I standardize my residuals, put it on a scale that kind of makes sense, we can really tell that this observation, which is observation 9, is way outside our 2 standard deviations. One thing I will note, and one thing about plotting, is that when I'm plotting this data here, I see this point, and it's kind of right on the -2, which is kind of near the rule, but also we have other points here. So this point here doesn't look too far away, even though it might be kind of close to our rule. So that's why we want to plot our data and not just use the greater than 2 kind of, if it's greater than 2, boom, because we might have data that is spread out. And again, theoretically, if you had 100 points, 5 of them could be sitting outside this area. Okay. So again, plot your residuals, plot your predicted, and look at it that way. For our leverage, here's our leverage points. Again, these are our hat values, our HIs, and we're looking for large values that are greater than our 2p over n. Again, in this case, p is going to be equal to 3, and is going to be equal to 25. P is 3 because we have 2 regressors, and then we also have our extra for the intercept. So what this is going to get us is a value of 2.4. And so that's what we're comparing to. And we see that observation, this is 9 because we're looking at the index, and this is observation 22. So let's go back real quick and look at observation 22. This one right here. We also know that, recall, leverage is extreme in the X. So if we were to look at these points, it would probably been easier if I plotted a scatter plot. Well, can't plot a scatter plot because we have 2. But maybe just kind of comparing, this 26 is a little bit further out than the rest of these numbers, and this one, 810, maybe not too far, but this one is a little bit further. And we can also notice that with 9, observation 9. So at least our metrics are making sense with our data. And then the last thing we want to look at is trying to detect our highly influential points. So again, we're comparing our highly influential points to 1. We can notice here, which is observation 9, is also, we would also flag that as a hit. Okay. We can also, as another way to check the impact of X, is we can fit our model with observation 9 in, and with observation with it not in the model. And we can look at that way. And that is what the other diagnostics kind of look at. But before I address the other diagnostics, I have a couple of remarks. So again, in this lecture, we talked about identifying outlying observations and the Y, the X, and then in both Y and X. Again, I highly recommend you don't just see an outlier and remove it. Investigate it a little bit more. If it is a valid point and it's unusual, maybe that's another way or place your research can go, or maybe we need to figure out some more covariates and stuff to investigate, to look at it. These rules of thumb that we have talked about today are a guiding kind of guideline. And so you always want to plot your data and making sure you're not kind of just doing a hard cutoff. You're looking for observations or residuals that deviate from the typical pattern that you see. There are often many borderline cases, and I think that's it. Let's just quickly, I'm just going to quickly go over kind of the additional diagnostics I have for you guys. Not a lot of this can be done in JUMP, I believe. It can be done in SAS or R. But the whole idea is this jackknife approach where you're going to delete an individual observation, refit the model, and then compare the fits from the fitted with the one deletion with the full data set. Okay. So that's kind of what these diagnostics down here, the difference in fit, you're looking at the difference between your predicted with the observation in it minus the deleted the prediction you would get when you delete that point, and then you standardize and stuff like that. For your difference in betas, you're looking at the betas with that ith observation in versus when it's not in. So that type of stuff here, you're looking at the different, not the difference, but looking at the ratios of the MSE without the ith versus with the ith observation. And so really it's that most methods in trying to detect hit points comes down to the general idea of we're going to delete this point and we're going to see how it affects our model. With that, you can now complete your homework questions related to outliers.